Okay. A little flustered. I had last minute things go wrong, of course, trying to get everything set up. But I think we're in business. How's everybody doing? Uh, let's get right into it. We're gonna be working on radio tools for radio navigation. My goal is next week we'll actually do some a flight planning exercise, but tonight we're just going to go over some of the tools that we can use for especially a longer range flight planning. One of them is radio navigational aids, having something to, and when we're flying from place to place, using just the chart, which is our primary means of navigation as a VFR pilot. To make sure we don't stray too far off course, our checkpoints have to be fairly close together because the longer you go without seeing something that you recognize, the farther you might get off course. So that can become pretty tedious and difficult. So having some other tools to help us out, kind of like having a tether rope to grab onto and pull our way along our route, really helps out and decreases our navigational stress. So first we're going to start off with just a brief history. Uh, for once flying became a viable tool for getting people and things from place to place, they shortly thereafter discovered that weather can be kind of garbage, so we need to have some way to deal with that. One of the earliest tools was something called an A&N course, and they had these stations posted along, and there were these 4 courses that you could fly to or from the station. And the way you were able to tell you were on course was by using the 2 Morse code letters, A and the letter N. And if you look on the, oh, hang on. I guess you can't see what I'm looking at. Bing. There you go. If you look at the diagram in the upper left-hand corner, you got the 2 letters A and N. You got N, which is a dash dot, and A, which is a dot dash. And the way that you knew you were on course was if you heard a solid tone. So if you got to the one side of your course, you'd hear one letter, and if you got to the other side, you'd hear the other letter. So imagine having to do your whole flight listening to this constant beeping tone in your head the whole time. Then came things called marker beacons, and what these were, these little transmitters that broadcast signals, mostly straight up, so that when you passed over them, you'd know you were over them, and could be able to say, I'm this place along my course line. Marker beacons are still in use today. A lot of them are being decommissioned, but they're still out there. They're part of the instrument landing system for IFR navigation. Then after that came the NDB back in 1924, the non-directional beacon. And so this was a signal that kind of just broadcast in all directions. And what we had is equipment on board that could triangulate that signal. If you look at some of the older photos of airplanes, there was this little round antenna up on the top of the cabin, and what that was a sensing antenna that they could use to home in on the non-directional beacon. And so you had to physically just hand crank it to turn it around to find where the strongest signal was and know where the station was relative to you. So wasn't long after that you had something called a non-directional beacon, which is what you see, or I'm sorry, the automatic direction finder, which its job was to automatically find the direction of the station relative to you. So luckily for you guys now, most non-directional beacons have been decommissioned. There's only a few out there. If aircraft have them, the equipment is old and oftentimes doesn't work. We removed our last automatic direction finder out of our planes about 2 or 3 years ago. But you had this piece of equipment that, if you were, oops, you're the little airplane here, and you had the needle which is pointing to the station. So the hard part of this one that people had trouble with was uh, knowing what direction you were actually flying was very important. So if you just happened to be heading north, then you could say that the needle is off your, or the station is off your right shoulder. Uh, but if you were heading east, the same would be true. It'd still be off your right shoulder. But where you were relative to the station was dependent upon your direction of flight or your heading. So if you were heading northbound, the station would be to your southeast. If you were heading westbound, then the station would be, off to the northeast of you. So it was all relative. So it's kind of confusing. It was a good tool. It took some practice getting used to it, and a lot of pilots hated it. Uh, but most of them be decommissioned. They removed all the FAA test questions. They have to deal with it. Uh, in the 40s there, you can see the VOR, which is the next one. That's the one we're going to be discussing in depth tonight. VOR stands for Very High Frequency Omnidirectional Range. So omni mean all directional, and the different ranges there. We identified 360 courses, but it was actually an infinite amount. But those were installed in 1944. In 2016, there were as many as 873 of them operational in the U.S., and they are going to be about 25 to 50% of them are going to be getting decommissioned over the next few years. So since 1944, the VOR has been the primary means of long-range navigation, especially for IFR flight. That is being replaced by GPS now, and that's what we're transitioning to, is a GPS-based system. The first instrument landing systems were installed in 1941, and they allowed a pilot to not only navigate and know that they were on course left or right, but you had a glide slope that can get you down to the runway. Those are, of course, still in use now, wide use. LORAN, long range area navigation. This was kind of like a ground-based version of GPS. There was antennas stationed across the country that you could have equipment on board that could triangulate your position. So this allowed for what we call direct-to navigation, saying I want to go from this point directly to that point without having an underlying radio station that we had to track. Those were decommissioned in 2010. So we had a plane that had that, and that worked for, well, up until 2010. We were still playing around with it. GPS developed in the 70s, approved for civil use in the 80s, and for air navigation it was approved in the 90s. GPS using, you got the satellites broadcasting a signal. You got your receiver, which is receiving those signals, and based on the broadcast location and the time, it can tell where the satellite was when it received the signal, and know then time, speed, and distance calculations. It can determine a three-dimensional position. There is some error associated with that signal coming through the ionosphere, and so normally you need 3 navigation sources to triangulate a position in a three-dimensional space, but for GPS we like to have 4. For IFR pilots, for instrument approaches, we have to have 5 satellites, be receiving 5 GPS satellites to be able to do an instrument approach. To help that out, we had the Wide Area Augmentation System, or WAS, which is a bunch of ground stations that helped because they're a fixed place on the ground, sending out a correction signal to your GPS receiver. You're now able to get, within about 1 meter, three-dimensional space accuracy off of your GPS receiver. To that, they've been adding the ADS-B, automatic, surveillance broadcast, which is now going to be sharing that GPS information from airplane to airplane and from airplane to air traffic control, with the intent of augmenting and in some cases replacing regular radar. ADS-B is required as of January 1st, 2020 to be operational on board your airplane for flight into any airspace that requires a transponder. Greetings from North Korea, said Brian. I hope you're having a good time. And we got Joe sitting down there in Florida, I assume still, enjoying life down there, hanging out on the beach, coughing on everybody. All right, next up, talk a little bit about GPS. So the GPS system consists of 24 satellites plus some spares that are up there. They are in 11,000 miles up. They are not in geosynchronous orbit, so they're kind of just scattered and going all over the place. GPS systems, especially for IFR navigation, have something called RAIM, or Receiver Autonomous Integrity Monitoring, which is autonomously monitoring the integrity of what you're receiving. So it's basically being able to say, I have 5 satellites in view, and so therefore I can do an instrument approach. Let's see, your typical sensitivity for a GPS is usually plus or minus 5 nautical miles, so each dot on your indicator is usually worth about 1 nautical mile until you get within 25 miles of the airport, and then it switches to what we call terminal mode. Big thing you need to know for your private pilot test is you got them 24 satellites. VOR, so your very high frequency omnidirectional range. You got a ground station. Now, because we operate in the airplane based on our magnetic compass and using magnetic north as our reference, the VORs themselves are also oriented to magnetic north. And so you got these stations all over the country, and we'll look at some of the indications of them and what they look like here in a minute. Although, again, it's sending an infinite amount of signals, we identify 360 of them, or radials, we call them. Radials radiate from the station. We call it courses going to the station. So there's 3 main kinds of VORs out there that we'll deal with for regular navigation. One is just a regular VOR. Another one is called a VOR DME, and DME stands for Distance Measuring Equipment. So this is equipment that's co-located with the VOR transmitter if we have the right equipment on board the airplane, a DME receiver, it will tell us, how far we are from the station. Most of the VOR classes you see there, you have your terminal VORs, which are pretty rare. They're only good for about 25 miles, but generally speaking, for navigation below 18,000 feet, which is where we're going to spend most of our time, if we are at least 1,000 feet AGL or above the ground, we should be able to receive a VOR up to 40 nautical miles away. When they transmit the signal, they transmit it in what we call, it's a line of sight, very high frequency transmission. So as it broadcasts out, it's actually going, kind of in all directions. So the higher you are, the farther away you're going to be able to receive it. Although you're still going to, the farther away you get, you're going to be losing signal strength as well. So in either case, VOR frequencies, oops, dang. Oh boy. technology. So your VOR frequencies are the 1082, or I'm sorry, 108.0 to 1112. Uh, the nice thing is on your Navcom, typical Navcom that we have in a radio, which is both a communications transmitter and receiver, is also a navigation receiver. The VOR frequencies won't fit in the nav in the com side, and the com frequencies won't fit in the nav side. So you can quickly tell if you're making a mistake as to where you're putting the frequency there. As we are currently in the process of dialing down the amount of VORs that are out there as we transition to GPS. It's going to be replaced with what they call a VOR, MON, or minimum operational network. The goal of the network is to trim the amount of VORs down to 585 by the year 2025, and it's going to be kind of still out there as a backup ground-based navigation system to support any military use, instrument approaches at different airports, mountain operations, and a backup for a loss of GPS navigation. So once you get down to the minimum network, you can expect to get navigational support from a VOR if you're at least 5,000 feet up. So right now it's 1,000 feet up. You should be able to receive a VOR, but to get continuous navigation reception from a VOR to VOR along your route, you're going to have to be about 5,000 feet up. In the airplane, we have the antenna, which is typically on the tail. It's the little V-shaped looking antenna on the tail. We have a receiver and an indicator. Looking at your indicator, there you have the OBS, or your omni-bearing selector, and that's where you're going to select what radials or courses you want to navigate to or from the station. So you're going to have a to or from indicator. This one now is indicating a to indication. You have your course deviation indicator here, and if you have the VOR set up correctly, you should always be turning towards the course needle. So if the needle is off to your left, and that means you need to go to the left to get on course. You have these dots here which are telling you how many degrees off course you are, and they go, each one represents 2 degrees, so out to 10, so 2, 4, 6, 8, 10. If you have a larger needle or dot in the middle, that the outboard portion of the dot is usually 2 degrees. And when we're doing navigation, I don't usually get stressed out unless I get more than 2 degrees off. I try to keep it within plus or minus 2 degrees to make sure I'm staying on my course line. If you're more than 2 degrees off, then depending on how far you are from the station, that could start to turn in some real distance off course, making your ground-based navigation a little more difficult. But also the VOR reception can sometimes be, I call it a little noisy, so that needle may be moving back and forth a little bit. So you don't want to respond to every little needle swing. So wait till it's 2 degrees off course and then start making your corrections to get on course. Probably one of the most difficult concepts people have with VORs is that the VOR does not account for the aircraft heading. The VOR indicator doesn't care which way the airplane is facing, and it's very important to understanding how to interpret the information that you're getting from the VOR. Whether you're going, so you can see all the airplanes here on this. They're all faced in different directions, but they're all going to be receiving the exact same signal on their VOR. Same thing down here at the bottom. Both of those are receiving the same signal depending on how they have it set up there. One of the things that you could do with a VOR that I'll demonstrate here in a second is that if you are receiving two different VORs, you could identify what we call the radial, or tune in the radial UR relative to it. So like if there's a, every time I touch that, it does that. It's so annoying. Let me do this here. Ding. Oh. So if you're unsure of your position, but you know you're receiving a VOR, you could tune in a VOR and figure out what radial you are off of it. And you can tune in another VOR, figure out what radial you are off of that one, and where the two lines intersect is your current position. It's called a VOR cross-check. One of the tasks you're going to be expected to be able to accomplish on your check ride there. When we're heading to or from a station, wind can start to blow us off course, and so we got to start making some course corrections. And so we have two things that we learn. One is tracking and bracketing. So tracking is just finding the heading that's going to keep us on our course line, and then bracketing is setting up. I don't want to turn any farther this way or any farther this way. I want to stay within those two heading directions there to make sure I'm staying on course and to make smaller corrections. So if you are, usually you want to initially parallel your course, and once you've paralleled your course, you watch for the needle to deflect. And if, say, it starts to deflect off to the right, then you would start you'd initially turn 20 degrees towards the right to get on course. So if your VOR is here and you're tracking to the station and you got wind blowing from that direction, your initial VOR indication would indicate that you're, the needle's centered and you're going to the station. But eventually you're going to get blown off course. And so that's going to show right needle deflection. So what we do initially is we turn 20 degrees towards our course line, and that's usually enough to get us back on course. And once we do get back on course, we don't want to turn back to our original heading because we'll just get blown off course again. So once we get the needle centered up again, we're going to turn back 10 degrees to leave in a wind correction angle. And then we just kind of watch for any further needle deflection. If it starts to get blown off course again, then we turn 10 degrees and come back 5. So initially it's turn 20, come back 10, turn 10, come back 5. And within a couple steps, you will have figured out what heading is getting the job done, within plus or minus 5 degrees. And that's important, especially if you're heading towards the station, because the needle is indicating, degrees off course. So 2, 4, 6, 8, 10. So if we're 10 degrees off course here, that same 10 degrees is only going to be a very small distance off course there. So the sensitivity of the VOR increases as you get closer to the station. And as you get to the perpendicular point, or get ready to cross the station, the needle becomes, just hypersensitive, and it will start kind of, deviating erratically off. I mean, it's still good to keep making small corrections, but you want to keep them fairly small. And eventually the needle will swing all the way off to the right or left, depending on which side of the VOR you're crossing. And your VOR, once you cross this perpendicular point, the VOR is going to go from indicating a to indication, and then it will flip to indicating a from indication on the other side. But if you start making, as the needle becomes more sensitive as you get closer, if you start making really big corrections, then this is typically what your flight path ends up looking like as you get closer to the VOR. So it's got to kind of dial down those corrections as you get closer. Keep making corrections, but you want to dial them down as you get closer. A little tool you could do if you want, you could determine how far off your course you are by using this little formula here. For every for every dot off course you are, you're 200 feet off course per nautical mile. So in an example here, give you 200 feet, 2 dots off course, and you know you're 15 nautical miles away. Then that means that you're 6,000 feet, or roughly 1 nautical mile off course. I've used that technique for determining how far off course I am exactly 0 times, I think, in flight, but there it is. Some other information that you probably won't need to know, but I'll just throw it out here anyway. There are different things that you could do to determine your position relative to a VOR. Nowadays, with everybody having, a GPS in their pocket, air traffic control, GPS in the airplane, it's becoming a lot less likely that you get lost. You may misplace yourself, but it's a lot less likely that you're going to get lost anymore. But before, when all we had to deal with was VOR, and we wanted to know how far from the station we were, there were some techniques that we could do to determine that. Distance measuring equipment is, again, co-located with a VOR. Your VOR transmitter sends out a Morse code signal every 10 seconds so that you can identify the station and make sure that you're listening to the right one. And if the VOR has distance measuring equipment, then every 30 seconds or every third one that you hear is the distance measuring equipment broadcasting. And so if you don't, if you hear a gap in the Morse code, that's telling you that the distance measuring equipment portion is not operational. It measures what we call slant range distance. So what I show here in the diagram is that it's not telling you what the distance is from there to there is. It's telling you what the distance from there to there is. So what that means is that the closer you get to the station, the more inaccurate the distance becomes. They figure about 1 nautical mile for every 1,000 feet up you are. If you cross the station at, and you're at 6,000 feet and you cross the station, the distance measuring equipment is going to read 1 mile because you're roughly 1 nautical mile from the station at that point. Other information that you can get from the distance measuring equipment is your ground speed, and that's measured as progress to or from the station. So if you're flying exactly perpendicular to the VOR where you're not going to it or from it, then your ground speed is going to read 0 on the DME receiver. Again, back in the 80s and even into the 90s, having a DME receiver was the bee's knees. Uh, Another display that again was really popular in the 80s and 90s is the horizontal situation indicator. And this, what this does is it overlays a VOR receiver on top of your heading indicator. And the way you're supposed to interpret the data coming off of a horizontal situation indicator is you're supposed to take the display that you're seeing and kind of just lay it flat on the ground. And what that's doing then is kind of telling you where you are relative to your course line, where you are relative to the station. The nice thing about the horizontal situation indicator is it indicates correctly whether you're coming or going, depending on, and so because it's got your heading integrated into it, it's a lot easier to interpret. It does take some getting used to, but you're going to find that learning to use the HSI is going to be fairly important because you're going to encounter airplanes that have now, primary flight display or glass cockpit displays. And when they use, when they display navigation information, they typically display it in the form of a HSI indication. So it's still going to be important to be able to, it is important to be able to interpret the HSI. One of our aircraft in the club has a horizontal situation indicator in it now. So a little mini glass cockpit version. Okay, so what I'm going to do now is we're going to try to learn to orient ourselves using just a display and to determine where we are relative to a VOR. Uh, 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 Okay, that doesn't want to play, so we'll just draw. That's fine. Oh, there it goes. Ooh. Okay, so in the middle of the screen, we have our VOR on the ground. You got our little miniature airplane there, and you can see the upper needle moving left and right. And if I were located right where the airplane is and I wanted to travel directly to the station, then what I'd want to do is center up my VOR needle to indicate correctly with a 2 indication. So you can see it's centered up with a 2 indication there. And it's saying that the course to get to the station is about 300 degrees. So what I would then do is turn to 300 degrees and start navigating to the station there. And depending on what the winds are doing, we're going to start to get blown off course. So you can see right now we've got a wind down there in the bottom right is was 230 or from the southwest at 20 knots. So you can see it's starting to blow me off course there. And looking up at the top indicator there, you can see that the needle is deflected off to the left, telling me that I need to go to the left to get on course. So what I would do then is make an initial correction 20 degrees towards the needle, and I would fly until the needle centered up. And as the needle centers up, you want to watch how fast the needle's coming in and kind of lead it a little bit. But as the needle center up, we're going to turn back 10 degrees to leave in a wind correction angle. Oop, I'm going to move my guy back here so I can keep going. And then what you do is just kind of watch for any further needle deflection, and if I started to get off course again, then I would turn towards the needle 10 degrees and come back 5. But usually within a couple steps, you can start to figure out what headings get the job done. So you can see it's starting to deviate a little bit to the right this time. So I'm going to go back 10 degrees, let the wind blow me back on course, and then I'm going to come back 5 degrees. And so now I've determined the wind correction angle that it should keep me pretty well centered. And so from there, I can just make small corrections, plus or minus 5 degrees. Now you'll notice as I get closer to the station that the needle starts to swing pretty rapidly there. That's because it's becoming hypersensitive. It just flipped to a from indication, telling me that I've just passed the VOR. And as it comes back in, I just continue navigating with my wind correction angle as I fly away from the VOR, still doing the same corrections. Flying to the right to fly to the needle there, or to the left. Now, if I didn't know where along my route I was, what I could use is, retune the first indicator to another VOR, or even better, if I have two VORs, I can tune that one into another VOR. You can see I've got another VOR down here. And to determine where you are relative to the station, I like to center it up with a from indication. And so you can see it centers up on the 050 radial from the station. And if I were to draw that line out on my chart, along with the line for the course I know I'm on, the 300 from the station on the top VOR, then the two together would indicate my current position along my route. We're going to go through some exercises to help us interpret the data coming off of the VOR. Well, do. Hey, leave stuff alone for a second, and it goes off and does its own thing. There, here we go. Pew. Okay, so I've copied this sheet straight from the figures book in the knowledge test, private pilot knowledge test guide. So these are VOR indications that you will see again on your FAA knowledge test or written exam. Not a sponsor. Okay. So let's look at figure number 2 to start off. Now, let's see. Let me see if there's an easier one. We'll go with figure number 9. So looking at number 9 down there in the bottom right-hand corner. What we have tuned in is we got a VOR tuned in to 030 or 30 degrees. We've got a from indication that tells us that we are going away from the VOR. And we got a CDI needle that tells us that we are exactly on course. And so what our job is to try to figure out is where in this quadrant are we? And to do that, what I like to do is draw out on a piece of paper just something to represent your VOR. We're going to draw out the 030, approximate it. Then I like to draw out the reciprocal radial, and what we call and the perpendicular point. So looking at the indication, I know that I'm going from the station, which means that I'm somewhere on this side. Looking at the CDI needle, it tells me that I'm right on course. It tells me that I'm somewhere right on that course line, which means that I'm, I could be anywhere along that course line, but that's where I am. I'm somewhere right on this course line here. Another thing, when you look at these VOR indications, it's very important that you pretend in your head that you're flying whatever direction is indicated on the VOR indication. So 9 has us somewhere up in that area. Now, if we go over to the next one, 8, 8 has us still dialed into the 030. This time we've got a 2 indication, and we're right on course. So we draw out our VOR, 030, draw out the reciprocal, draw our perpendicular point, and then we just look and see where we got. So we're still going to the station, so we're flying to the station, so that means that we're somewhere on this half because we haven't crossed the station yet. We're right on course, which means that we're somewhere right on that course line. This doesn't have any eraser. So that puts number 8 somewhere down here. I'm going to skip number 7. Let's go to, let's see, let's do another, all the rest are 210. So this is where it can get difficult, and I feel like they did this on purpose. But anyway, let's look at number 5 here. So number 5 has us with 210 dialed in, still going to the station, and we are right on course. So what we want to do is, on our scratch paper, draw out our 210 degrees, draw out the reciprocal line, and then draw the perpendicular point. Now, again, you got to kind of turn your head sideways here to visualize this, but you got to imagine that you're flying 210 degrees. And because we're still going to the station, that means we're still on somewhere on this side of the VOR. We're not past the station yet. We're still going to it, so that means that we're exactly on course. So that means that we're somewhere right on this course line right here. So we're actually in the exact same position as number 9 is. Just have the VOR tuned in the opposite direction. So that's number 5 is also there. Oops. All right. Now if we look at number 6, so we still have our 210 dialed in. We draw out our perpendicular point. We're going from the station this time, which means that we're somewhere, if we were traveling 210 degrees, we're going, flying in this direction, and we're past the station, so that means that we're going to be somewhere on this half. We have to go to the left to get on course, so again, if you turn your head around, and see that you got to go to the left to get on course, and that means that you must be somewhere in this quadrant over here, because that's where you'd have to be if you had to go to the left to get on course. So that's where number 6 is somewhere over there. So number 6 is somewhere over here. Now, let's look at, let's see, 2 is a pretty easy one, because that one we're dialed in at 210. We're going from the station, so again, we pretend that we're flying this direction, 210 degrees. We're going from the station, so we're past the perpendicular point. So we're somewhere out here, and we're right on the course line, which means that we are right on the course line. So we're in the same, along the same line as number 8 there. So number 2 is also down here. Number 1, we have 210 dialed in. We're still going to the station, and we have to go to the right to get on course. So, drawing our radial out and our perpendicular point, we're still going to the station. So if we pretend that we're going that direction, and we're still going to the station, it means we're somewhere on this half. We have to go to the right to get on course. So again, turning your head sideways there, we can see that if I had to go to the right to get on course, it means I'm somewhere down in this quadrant over here. So that'd be number 1 there. So there's that. And we got number 1 is somewhere over there. Number 4, we're going 210 degrees to the station, and we have to go to the left to get on course. So we're still going to the station, so that means we're still somewhere over here. We have to go to the left to get on course, which means that we must be somewhere over here. So that's where number 4 is. Somewhere over here. And let's see, that leaves us number 2 is down here. That leaves us number 3 and number 7. Now, I left those off purposely because they are the ones that people have the most trouble with. So, looking at number 3, again, you want to pretend that you're going whatever direction is indicated there. So you're going 210 degrees. The problem is we don't have a to or a from, so that means that we are somewhere on this perpendicular line. Because that's where it flips from to from. So if it hasn't flipped, that means we're still somewhere on that line. And if we pretend that we're going 210 degrees, so we're traveling in that general direction, and we have to go to the right to get on course, then that means that we are somewhere over there. Now, that's where number 3 shows us. Somewhere over here. And if we look at number 7 last, you can see that we have 030 dialed in. we're neither to or from the station, which means that we're somewhere on the perpendicular point, and we have to go to the left to get on course. So we pretend we're going that direction, and we have to go to the left to get on course. We're somewhere on this perpendicular thing. If we're going 030 and we have to go to the left to get on course, and that means that we are somewhere on this side. So we're actually in the exact same area as the other one, number 3, has us up there. So those are probably the most difficult ones that people have trouble with, is the perpendicular point. I know there's one FAA test question in particular that asks you to use a VOR chart and asks, which one of these options tells you that you're over a certain town, and the answer is number 7. But anyway, you want to practice with that, and that's what we get to do now. So if you have some scratch paper handy, what I'm going to do is give you a few to go through yourself. I made them a little bit easier to get started. So here we want to know which airplane coincides with the VOR indication. So we're going north. We have to be going to the station, and we have to go to the left to get on course. So again, I highly recommend drawing out your little VOR. Draw out where you think the airplane is, and then look up at the chart to see which one represents where you think you put it. Okay, so just to show you really quick. So we're dialed into north, which would be up here, 0 or 360. We're still going to the station, which means that we're somewhere down here. We have to go to the left to get on course, which means that we're somewhere over here. And so that leaves us airplane D. Now again, the confusing thing is that we see the airplane D is facing the other direction. But you got to keep in mind that the VOR itself does not care what direction the airplane's facing. So letter D is the answer there. Here's another one for you. So which letter represents the VOR indication? So we're tuned to north or 360. We're going from the station, and we have to go to the left to get on course. So go ahead and take a second and figure that out. Okay, I'm going to start working through it. So hopefully you're a little bit ahead of me. So we're going north is where we got tuned in. We're going from the station, so that means that we're somewhere on this half. We have to go to the left to get on course, which means that we're somewhere over here, which means that airplane B is the only one that matches those representations. Oops. All right, well, let's try another one here. So that was B. Now this one's a tough one because we're not going to or from the station. So again, always pretend you're going whatever direction you have dialed in on the VOR. So go ahead and take a moment to see which airplane you think represents this indication here. Fast typing again, I see, Nancy. Too fast, too fast. think we're doing all right now. All right, let's see what we got here. So, we're going north. We're neither to or from the station, which means that we're somewhere on this perpendicular line. We have to go to the left to get to the station, so that puts us somewhere over here, which puts us at airplane C. And that is correct. Good job. All right. Now we got one here a little bit harder. You're going to have to turn your head sideways maybe a little bit. So we're going west. We're going to the station, and the needle is off to the right. So again, the key thing is to make sure you pretend that you're flying the direction indicated on the VOR. All right, I see you guys throwing some answers out there, so let's see what we got. So we're heading westbound, so that means that we're flying in that direction. We're going to the station, so that means we haven't got there yet, so that means that we're somewhere on this side. We have to go to the right to get on course, which means that we're somewhere over here. And that leaves us at airplane D, which I see you guys are getting there, so good job on that. All right. Now you get to turn your head the other direction. So go ahead and try to work this one out. Going eastbound to the station, and we have to go to the left to get on course. All right, looking good. Let me see. Let's see what we got here. So we're heading eastbound, which means that we're traveling in that direction. We're still going to the station, so that means that we're somewhere on this side. We have to go to the left to get on course, which means that we must be somewhere over here, which leaves letter E as the airplane that we're looking for. Bing. Even more difficult. Uh-oh. So here we're heading 135 degrees, which is that guy right there. So we're heading 135 degrees. We're still going, this time we're going from the station. And we have to go to the right to get on course. So let's see what you come up with there. All right, we got some answers popping up there. Let's see what we got here. So we're heading 135. We're going from the station, which puts us somewhere on this half. We have to go to the right to get on course, so if we turn our head that direction and see that we got to go to the right to get on course, that puts us somewhere over here on this side, which puts us at area C. So good job on that. All right, here's another one. See you guys throwing answers on the text thing is really, really brave. I'm glad to see you guys doing that. It's a good way to build some confidence. Throw yourself out there. All right. So let's see what we got here. So we're flying. Ooh. Uh, eh. All right. So we're flying 135 degrees. So there's 135. So we're flying in that general direction. We're still going to the station, which referencing the perpendicular point, we're still on this half, and we're right on course. So that means that we're somewhere right on this course line, and so that means that A is the only one that could be there. Again, it throws you off because it's facing the wrong direction, but we're still going to the station. It's always important to make sure you turn your head or your sheet of paper in the direction of flight, and that will help you draw it out faster and be less difficult there. Okay. Now the next thing we're going to go over is the E6B flight computer. Uh, Now there are electronic versions available, uh, and I think I've mentioned before with those, you know, when we're not comfortable with something, you know, we try to find some way to compensate. So we have these electronic flight computers, which are great and all. The problem is, you know, once you get your private pilot certificate, you know, your flight computer just becomes a dead battery storage device. You know, once you get your pilot certificate, you're going to probably be using apps and other tools. Uh, so I like to just stick with the no school, like the old school electronic flight computer. It does take a little getting used to get uh, practice with it, but it doesn't require batteries, only one thumb to operate, and I've used it in flight a few times, even with having a GPS on board. If you know how to do some of the basic calculations, it's faster to do it there than even type stuff into an app or a computer. Hmm. Let's see. Let me find something here real quick. All right, I'm going to pull up a practice tool I have. That you're going to need some scratch paper handy. Uh, hmm. Sorry. Let's see. There we go. Sorry. All right. Okay. So on our club website, if you ever want to practice this stuff, down there at the bottom, there's a button that says Flight Syllabus. You can click on that. That's going to pull up this page here. You don't have to have a login to do the E6B flight computer practice. But just click on the button there, and it's going to give you some practice exercises here on time, speed, and distance calculations. I also gave you some workbook pages with the answer key for you to practice on your own. Now the E6B flight computer, you can see it's got two dials that, when they're lined up together, everything matches exactly. We got different scales there. We've got the black scale on the outer, that we call that the outer scale. We got the first scale on the inner dial, we call the inner scale. And then we got the, if you keep looking down there, you got the 10, and then the 1 hour and 40 minute there. That'd be the inner scale. There's there's a lot of different calculations that you can do with the flight computer. You could do things like basic uh, do, 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 do. You do, just to give you an idea of how it's working, do things like basic math. So if you wanted to know what 10 divided by 2 was, uh, uh, you might write that out like 10 over 2 equals some answer over 1. And what we're trying to do is solve for that. And so that's something that the flight computer can do. We just put what we know here. This would be the outer scale. This would be the inner scale. And you always want to set up your known amounts first. So if we pull up the flight computer here, you can see I got that 10 on the outer scale. I can set up 2 underneath that. Now, you're going to see that I have 20 underneath there, but each of those digits can represent multiple different numbers. It could be 20, 2 million, 0.2. You have to set the amount of significant digits that you want in your head. But once you have that basic ratio set up, then we find our answer over top of 1, and on the E6B, that's referenced by the number 10, and you're going to see that that's blackened in because it's a common reference. And so once I set up my ratio, I just look for the number 10 on the inner scale down here, and you can see opposite the number 10 I have the number 50, which would represent 5. So that's how you can do division on there. You can also do multiplication. Let's see. So if you wanted to multiply something, let's say that we wanted to do 3 times 5, then what I would write that up as is 3 over 1 is equal to 5, and then my answer would be down there. Well, let's see. So I set up my 3 over 1, which would be 3 over 10, and that's going to give me all the multiples of 5 that I want, actually. So I find my 3 on the outer scale. I set up the 5 on the inner scale. Oh, I'm sorry, the 1. And once I have that, I can figure out all of my different multiples. So for example, 3 over 1 is equal to 3. 3 over 2, you can see you got the number 6 on the opposite side. 3 over 3, you got 9. 3 over 4, you got 12. And so you've got all the multiples of 3 just waiting for you. Now, when we're doing aviation calculations, we're doing really the same thing. We're just setting up a ratio. And the basic ratio for these calculations is we go speed. And whenever we talk about speed, speed is a rate. So it's something per something. And in this case, it's per hour is typically what we're talking about. More specifically, it's per 60 minutes. So speed always goes over the 60 mark. And then we have distance over time. And once you know that little ratio there, then if you have any three of those elements, then you can solve for the last one. So for example, let's say that you knew how fast you were going, you knew how far you have to travel. What you don't know is how much time, how long it's going to take you to get there. Well, these are the, because 60 is a constant, those are the three elements that you have waiting for you. And so that's what you would set up. You would set up the two that you know, you'd set the speed over top of the 60, and then you'd read your answer underneath the distance that you have there. So we're going to do a little example here. So we're going to figure out time. Well, so once you have that out there, just click go, and it will give you some parameters. So it says that we're going 64 miles per hour for 92 minutes, and we want to know how long that's going to take. So anytime you know your speed, that's the first thing that you want to set up, because that speed is always going to go over the 60. And you'll notice that the 60 mark, you got 55, 60, and then 70 there. The 60 mark has that little triangle on there. So first thing you're gonna do is set up your speed. So speed goes over the 60. So I set that up to my speed here of 64. Yep. All right. And then we know, the other thing we know is that our distance is 92. Now, we read distance on the outer scale, but if I forgot that, how do I know? Well, what you can do is right on the front of your E6B, it gives you the ratio right there. So it tells you where everything is located and how to set it up for you right on the E6B. So if you forget everything else we talked about tonight, just remember to look at your E6B. All right, so distance is on the outer scale. So we know our distance to be 92. Unfortunately, on this app, I can't rotate that. So you can on yours, and I suggest doing it. But anyway, we find 92. And if I read opposite of 92, I get a time of 85, roughly 86 minutes. And if I keep reading down to the inner scale, it converts that 86 minutes to hours and minutes. So it would be 1 hour and 26 minutes. So if I type that in here and click check, it tells me that we got it right on. So we're going to try another one here. Oh, let's keep it reasonable for now. There we go. So here we're going 84 miles per hour, and we're traveling for 131 miles. Now, some key things to help you check your answers to make sure you're getting the right kind of numbers is if the distance you're traveling number is higher than your speed, then it's taking you more than an hour, because you're only going to be going the 84 miles in that hour. So it's going to be more than an hour. So that's a good double check to make sure you're getting the right answer. So the first thing we need to do is set in our speed. So I set my speed 84. Over my distance, or I'm sorry, over the 60 mark. And then I got to find 131 miles on the outer scale. So that's the black scale there on this one. So you can see there's 130 or 13. 131 is just going to be halfway between the two. The other thing you need to pay attention to is the scale in between the numbers. Always make sure you count how many tick marks are between, like in this case 13 and 14. We've got 10 tick marks, but sometimes that scale changes a little bit, which can change your answer a little bit. So make sure you check that out. So we look at 131, and I'm getting about 91, 92, 93, about roughly 94 minutes, which continuing down to the inner scale is telling me it's about an hour and 34 minutes. So that's what we'll try out. So 1 hour 34, click check, and there we go. All right, let's try another one. Try a little harder one here. So here we got some bigger numbers. So we got 234 is our speed and 208. Now, because 208 is less than 234, then we know our time is going to be less than an hour. So that's something to keep in mind as we look up the answer here. So first thing we need to do is set our speed. So I need to find 234. So down here I've got 23, which I'm going to use as 230. And look at the scale between those two. That's 2, 4, 6, 8, 10. So the scale's changed a little bit, so that's going to be 232, 234, right about there. We're going to lock that down. And then next we need to look up our distance. Distance shown on the outer scale, and we're looking for 208, which is right close by. So there's 200, there's 210, so 208 is going to be the fourth tick mark between the two. And we look down there, we've got 50. Again, look at the scale between the two. We got 50 and 55, so that means that the longer tick marks are each going to be worth 1. So that's 51, 52, roughly 50, about 53 minutes. So what we'll call that. See how we do. All right, there we go. I'm going to let you guys get ahead of me on this one and try this one out yourself. So just try to use your E6B, see if you can come up with a answer. So we're going 71 miles per hour, and we have to travel 294 miles. First thing you're doing is setting the speed up over the 60 mark. So speed is on the outer scale, index mark for 60 on the inner scale. Then you're going to find 294 as a distance is right on the outer scale. You're going to read your answer on the inner scale. The number is on the bottom is more than an hour, so we know it's going to take us more than an hour to get there. All right, so let's do this one. So let's first set our speed to 71. We need to find 294 on the outer scale. So there's 250, and then we got some tick marks there that we can read. The longer ones is 260, 270, 280, 290, 294. So it's going to be about 2 hours or 250 minutes, which should be 4 hours and 10 minutes is what I'm getting. So let's see how that goes in there. Oop. So we got 4 hours, 10 minutes. I got a couple of people that look like they have some pretty good answers. So be right in the ballpark there. So we're doing good. All right, very good. Let's try one more of these. So here we're doing 152 miles per hour for 49 miles. 152 miles per hour for 49 miles. Good job, guys. Those good answers there. Okay, so we're doing 152 miles per hour. So again, it could be regular miles per hour, nautical miles per hour, just whatever. Just want to make sure that whatever speed you're using is the same as the distance measurement. So looking at the scale, we're going to set that to 152 there. We're doing 49 miles, so we're going to look up 49. There's 40, 45, 46, 47, 48, 49. So it looks like a little less than halfway between 19 and 20. I always try to round uh, just to the closest minute. We don't have to be any more accurate than that. Now we know the number is going to be less than an hour because the distance is less than the speed there. So again, just watch out for that. It's a common trap that you got to be careful of. Thank you for the 19.2 minutes. Nice. But yeah, I'm liking that 19 minutes. So I'm going to type that in here. 19, click check. All right. So next we're going to move on to speed. So here in this example, we know how far we've traveled, and we know how long it's taken us to get there. This is well, I guess we have Google Maps to tell us that now, but back in the day, this was always fun to do on your road trips to try to figure out what your average speed was and figure out how long it's going to take you to get somewhere. But anyway, you know how many miles you've traveled, and you know how long it's taken you. The question is how fast you're going. So this is actually a useful tool in the air. So if, you know, based on your flight planning, you expected it to take it a certain amount of time and you find that it's taking a little longer, well, you can measure the distance between 2 points along your route, time how long it takes you to go from one point to the other, and then you can figure out your new speed along the ground or ground speed, which you can then factor into, you know, the rest of the distance that you have to travel. So you can see if maybe a fuel stop is called for, or if you have enough extra fuel to get there even though you're going a little slower. So this is a useful one here. So here we're going, we're apparently going to be in a hot air balloon, but anyway, we'll go ahead and figure it out anyway. So we're going 39 miles, and it's taking us an hour and 20 minutes. So looking at our ratios here, uh, so looking at the ratios here, in this case, we know our distance and we know our time. What we don't know is our speed. Uh, so what we do is we set up the two numbers that we know over top of each other, their distance over time, and then we're going to read our speed is going to be read over top of the number 60 there, or the arrow. So we find our distance, 39 on the outer scale. There's 35, there's 39, and then what we're going to set over underneath our 39 is our time, which is hour and 20 minutes, which is the same as 80 minutes there. So we set our 39. We got 35, that's 36, 37, 38, 39. over the hour and 20-minute mark. And then we just find the 60, and we can read our speed there. So we got 25, 26, 27, 28, roughly 29 miles per hour. So we'll check that out and see how we did. Nice. All right, let's let you guys try one here. So we're doing a distance of 51, and it took us 21 minutes to do it. So here, if the, well, you can see our speed is, or our time is only 21 minutes, so let's see what we got. Hopefully you guys are figuring that out. So we set what we know. Again, we're going to set our distance over top of our time. So it's going to be 51 over top of 21. So we find 51 on the outer scale over top of 21 on the inner scale. And then we just read our answer right over the thing there. Our speed is going to be higher than that because this is less than 60 minutes. So we can put in our answer then. It looks like to me about 145 is the way I would interpret that. Or to be even more exact, Tim, 146, which is what the answer was exactly. So good job there. Let's try another example here. Nah, I don't want to do that one. There we go. So here we're going 77 miles for, and it took us an hour and 41 minutes to do it. So it sounds like we're probably going pretty slow again. If the number is more than 60 minutes, then you know your answer is going to be less than whatever your distance is there. I'm sorry, more than. Oh, less than. Sorry. Okay, so to solve this, you're going to set your distance over top of your time, and then you're going to read your answer over 60. So we've got to find 77 on the outer scale, and then we're going to put an hour and 41 on the inner scale. There's an hour and 41 over top of 77. So there's 75, 76, 77. All right, and then we're going to read our speed. I'm getting about 46. Looks like you guys are getting similar answers there. So let's try that 46 out and see how we did. Oh, I typed in 56. Well, you can see here on the little tutorial guide, if you type in a wrong number, it'll let you know. It gives you a little bit of tolerance there because this isn't an exact science. But again, you only have to round to the nearest mile is close enough. So that's how you determine how fast you're going, or your ground speed. Another thing that you can use E6P for is along the same lines is we know uh, how long we've been traveling for, and how fast we're going. The question is, how far have we gone? So using our so again, we got our speed over 60, and we have our distance over time. So in this example, we know our speed, so we're going to know those two numbers, and we know our time. And what we're going to solve for is the distance. So you always set the two up that you know, so you're going to set your, that match up over top of each other there. So we're going to set the speed over top of the 60, and then we're going to read the distance over top of time. All right, so let's try our example here. So we're going 212 miles per hour, and we've been traveling for an hour and 11 minutes. Yes, Nancy, don't doubt yourself on those answers there. Don't second guess too much. All right, so we know how fast we're going. So anytime you know how fast you're going, that's the first thing that you want to set up. Because that's just going to be your speed over top of the 60. So we're going to set up 212. There's 200. That's going to be 210. That's going to be 212. All right, so we got our speed set up over the 60. And then we're going to read our, we know how long we've been traveling, so we're going to read under the hours and minutes. So we find an hour and 11 minutes. Down here's there's an hour and 10, so one tick mark past that. Says it looks like we've gone about, I'm going to guess 250 miles. Again, because our time is more than 60, then the number is going to be higher than your speed number because you would have gone 212 in 60 minutes. So if it's over 60, it's going to be something higher than that. So double check for yourself. So I'm going to guess about 250 miles. 251. Darn it. Okay. All right, so go ahead and try this one yourself. So again, you know the speed, so you're gonna set that over top of 60. You know how far you're going, so that's gonna be on the time scale, which is the inner scale, hour and 22 minutes. In fact, because it gives it as an hour and 22 minutes, you can look it up two different ways. You can convert it to minutes and call it 82, or you can just leave it at hour and 22 and just use the inner scale to find that. All right, we got some numbers coming in, fast and furious. So let's see what we got. We're going 54 miles per hour. So that's over here. So we're going to set that in there, 54. And we know we were going an hour and 22 minutes. So there's an hour and 20, or again, we could call it 82. So it looks like about 71, 2, 3, 4, about 74 miles. It looks like getting some of those numbers in there. Let's try it out. 74. Click check. And we're good. So you want to practice these. I highly recommend practicing. The better you are at doing these, the easier our exercise is going to go next week where we get to do some time, speed, and distance calculations during our flight planning exercise. But this also just helps cut your flight planning down. Just a typo there, Tom, I'm sure. Well, next thing we're going to look at is we're going to flip the E6B over and look at the backside, which everybody loves. And I have one here, true heading and ground speed. So, what the backside is used for is determining two numbers that we're searching for. One is called our ground speed. We want to know how the wind is affecting our flight, and the other is called our wind correction angle. So, how many degrees do I need to turn to the left or right to compensate for any wind drift errors so that I can stay on course. So some information that we need to know to be able to figure that out is we need to know what the wind direction or the forecast wind direction and velocity is. We need to know what direction we're trying to fly, and we need to know what our planned what we call true airspeed is, or speed, how fast we're truly plan on going across the ground. And once we have that, then we can use that information to find our ground speed. Now, I don't have it on my sample E6B here, but your E6B should have some instructions on the top of the card up top there that to figure this stuff out, you just need to follow the instructions. That's going to be key. So I'm going to work through a couple examples here with you. So here we got the winds are coming from 270 degrees at 25 knots. We got a course that we're trying to fly of 311 degrees, and we're planning a speed of 83 miles per hour. Oh. All right, looks like my uh, all right, my webcam decided it doesn't want to play for right now, so that's all right. I get to look at my pretty mug for a minute. Uh, anyway, let's go through this. So, what you want to do is the first step should be to set your wind direction under the thing up top is called your true index. So in this example, our wind direction is 270. So we're going to set that 270. All right, the next thing we want to do is we want to make a mark on there that represents the wind velocity being 25. So what I recommend doing is sliding your E6B until the grommet in the center is right over top of the 100 line going across there. And that's just going to be used as a reference, so that, just a tool for measuring a distance. Because then what we want to do is, with a pencil or something that we can erase, we want to make a mark up 25 up from that center point. So we're just going to count out 10, 25, and then we're going to make a mark right there to represent the wind velocity. Once we have the wind velocity mark down there, then what we want to do is rotate the dial to get our true course, set our true course under the true index. So in this case, we're doing 311 degrees. So we set that to 311, 10, and 11. Okay? Then what we want to do, and this is the part where you got to be careful, because this is where everybody makes the most common mistake here, which is we need to slide the wind velocity mark, which is the mark that you made, down to the line that represents our true airspeed. So our true airspeed is 83. So what we're going to do is we're going to slide that mark down, and you can see there's, I don't know if you can see, let's see, there's 80. Oop. There's 90. So that's 2, 4, 6, 8, 10. So it's going to slide it to right between the first and second one there. That's 83. Once we have that there, we can read our ground speed under the center, the grommet underneath the center there. So I'm getting about 62. So I'm just going to put that in there at 62. Now, to figure out our true heading, we need to know our wind correction angle. And so you have these angular lines going left or right of center, and they're labeled down there. You can see 10, 20, 30, 40. And what we do is we count the angular degrees off the center line that the wind velocity mark ended up. So I'm counting about 12 degrees to the left. So if it's to the left, that's going to be a minus 12. If it's to the right, that's going to be a plus 12. So I take that minus 12 number that we have here, and I'm going to subtract that from my true course. So 311 minus 12 is going to be about 299. And that's going to be my true heading. And then we click check here, and we see that we got pretty close, within a degree, and right on with the speed there. All right, so let's walk through another example here. All right. So here, starting over, we're going to set our wind velocity to the true index. So I'm going to set that to, wind velocity. Wind direction under the true index. So I'm going to set that to 170. We've got a wind speed of 16 knots, so I'm going to, again, slide that card down until the 100 line is right under the center. And then from the center, I'm going to count up 16 tick marks and make a mark there. So there's 10, 12, 14, 16. Make my mark right there. Once I've made my mark, then I need to rotate the dial to my true course, which is 269. So I'm going to set oops, settle down. That's 16. There. So I'm going to set this to 269. This looks like almost a direct crosswind there. Once I have it set to 269, I'm going to slide the card so that the wind velocity mark is on my true airspeed line. So true airspeed we have is 164. So I'm going to slide that down to, there's 150, 162, 164. So I'm getting a ground speed here of about, let's see, we'll call it 166. So I'll put that in there, 166. And then to figure out my true heading, I got to figure out the angular difference. So I count how many degrees it is. So I'm getting about roughly -5, maybe 6 degrees, somewhere in there. 1 degree off one way or the other isn't going to make a huge deal, but that's going to be a -5. So I subtract that off of 164, and I get 159, we'll call it. And then we'll check our answer here. Oh, I'm sorry. I subtracted my 5 off of the wrong number. It had been 269 minus the 5 or 6. So yeah, it would have been 263. So hopefully you guys didn't make that same mistake I did there. Okay, I'm going to let you run through one on your own here. So I'm just going to click the go. See if we get something interesting here. Okay. So just follow the directions on the back of the, or on the top of your card there, step by step. For 2 numbers, we're looking for a ground speed, and then we want to know that wind correction angle so that we can factor that into our true course of 69 degrees. Okay, I'm going to start working through it. So first thing we want to do is set our wind direction under the true index so we get 300. We want to set our wind velocity up from the center, so we're going to slide that card until the 100 is underneath the center grommet. And then we're going to make a mark up 25 from the center. Then we're going to rotate the true index or a true course under the true index. So that's 69 degrees. So there's 50, 69. And then we're going to slide the wind velocity mark to our true airspeed line of 156. So there's 150, 246, so 160, 56. And that's showing, it looks like a little bit of a tailwind here. So we got a ground speed of 170. And then looking at our true heading, we've got an angular difference of minus 5, 6, so minus 7 degrees. So we're going to subtract 7 degrees from the 69, so that gives us 62. Looks like Tim was right on there. So we're looking pretty good. So again, those just take practice. You got to work through some examples. The last thing we're going to look at before we call it quits is figuring out true airspeed using our E6B. So for that, we need to go back to the front side. And if you look, usually in the bottom right-hand corner, you'll see two numbers there, or you'll see two things there. You see TAS over top of CAS. That's true airspeed over top of calibrated airspeed. What that's telling you is that you're going to read your true airspeed over top of your calibrated airspeed. Now, true airspeed, recall, is calibrated airspeed corrected for non-standard temperature, pressure, altitude, that kind of stuff. So to figure out true airspeed, the first thing we have to figure out is our density altitude. And to make our life easier today, we're going to already have that figured out for us. So if we just use the thing here, I'm going to click a thing. Here's again an example. So we've got a density altitude of 3,000 and a speed of 93. And calibrated, or I'm sorry, a true airspeed of 93, and what we want to know is what is the calibrated airspeed. Now you got to watch out because on the example here I switch those around a little bit so you can practice figuring out either one. So somewhere on there up towards the top you should have a density altitude scale, and if we already know our density altitude, all we got to do is dial it in there. Now you can see that the scale is really tiny, so you just got to do your best to get it as close as you can to what your density altitude is. So we know our density altitude here to be 3,000 feet. So I'm just going to set that. There's 1,000, 2,000, 3,000. I'm going to set that to 3,000 feet. And then I know my true airspeed is 93, and what I want to know is my calibrated airspeed. So true airspeed is red on the outer scale. So I find 93 on the outer scale. 91, 92, 93, and I'm reading my calibrated airspeed on the inner scale is 89. So this is saying that if I was at 3,000 feet, had a true airspeed of 93, my calibrated airspeed should be 89. All right. So let's try another example here. This time we know our calibrated airspeed, and what we're searching for is our true airspeed. So again, we already know our density altitude is 8,200, so we just set that in the density altitude scale. So there's 5,000, 6,000, 7,000, 8,000, and we'll give it just a little bit more for 8,200. Try to get as close as you can. And then we read our calibrated airspeed on the inner scale, true airspeed on the outer scale. So calibrated airspeed is 71, and our true airspeed looks like is going to be about 80. So if we were indicating or calibrating about 71 at 8,200 feet, we'd actually be going about 80. And then it's that 80 number that we would want to make sure that we used for our flight planning. Good job there, Nancy. Let's do one more of these, and then we're going to do one more example of the other one. All right, so here we're at 3,100 feet. We got a calibrated airspeed of 117, and we want to know what our true airspeed is. So, go to our density altitude window, set in 3,100, so there's 1, 2, 3,000, and just a little bit more for 3,100. We're going to find 117 calibrated airspeed, goes on the inner scale. 15, 16, 17. So I'm getting about 120, looks like about 122. Now there is a thing here that talks about setting true airspeed and density altitude. Again, some directions right on your E6B to remember that they exist. So here it says to set your air temperature over top of your pressure altitude, and you're going to read your true airspeed over top of your calibrated airspeed in the window there. So looking down at this last one here. So this one's kind of like the full boat. First thing we got to do is we are given our altimeter setting, our true altitude, and our temperature at that altitude in Celsius, and we know our calibrated airspeed. So we're going to use all those numbers there to figure out our true airspeed. The first thing we have to do is figure out our pressure altitude, and unfortunately that's not something that the E6B is good at figuring out. But we can just use our what we learned before and take our 29.92 and 3038 and find the difference between the two. We're going to multiply that by 1,000 equals 460. The pressure is higher than standard, so that's just like going down because pressure gets higher as we go down. So that's going to be a minus 460 that we're going to subtract from our true altitude of 7,600. So we take our 7,600 minus our 460. Gives us now a pressure altitude of 7,140 feet. Now, to use our E6B to figure out our density altitude, you can see you got your little window over here. And what we got to do is set our temperature over top of our pressure altitude. Now, a common error people make is the temperature. You can see that the plus side goes to the left, where the minus side goes to the right. So a lot of people do that in reverse, and they end up with the wrong number. The other thing to understand is that the numbers shown here, 0, 5, and 10, those are in thousands of feet. So that's 5,000 and 10,000 feet there shown in that little window. So we know our temperature to be 18 degrees. So we find 18 degrees, and I can't do it here, but what I like to do is with a pencil or something, put a little tick mark by the temperature of 18 degrees. So that's going to be counting from the 0, we got 5, 10, 15, 20. Make a little tick mark on your E6B right around where the 18 mark would be. And that's going to make it a lot easier, because then once you have that little tick mark at the 18 degrees, you just need to rotate it until that tick mark is over top of your pressure altitude of 7,100 and something feet here. So I take the 18, set it over 7,100 and some change there, which is going to tell me that looking in the density altitude window, that my density altitude is about 9,000 feet. But we don't really need that for this answer. But once we have that set in there, though, we can now go to our 83 calibrated airspeed and read on top of that to get our true airspeed. So 83, reading on top of that, I'm seeing about 95. So we're going to try 95 there. All right, we're going to do one more example here. Try to stay ahead of me. And then we're going to call it a night. So I'll give you a second to start working that out. So first thing you need to do is use that 3064 to figure out, and the 4800 to figure out your pressure altitude. So you got to figure out your pressure altitude first. Mm. Okay, hopefully you guys got a good head start there. So first thing we're going to do is figure out our pressure altitude. So we've got a pressure of 3064. And we're going to find the difference between that and our standard pressure of 29.92. So we got our 2. We're going to multiply that by 1,000. That's going to give us 320. Sorry. I got I carried away with myself. So about 720. And pressure is higher than standard. So that's going to make that a minus. And we had a true altitude of 4,800. So we're going to take our 4,800 minus our 720. Which is going to give us our, let's see what we got, 4,080 feet. So that's our pressure altitude. So we're going to use that plus our temperature to figure out our density altitude. So looking at the E6B, we're going to use a temperature of 5 degrees. So again, I recommend making a little tick mark by the 5 degree point on the temperature scale to make sure you get the pluses and minuses right. We're going to take that 5 degree tick mark and we're going to rotate it to 4,080 feet. So there's 5,000, there's 4,000, and a little bit extra there. And once we have that dialed in, then we have our calibrated airspeed of 181. We're going to find that on the inner scale. And we're going to read on the outer scale to figure out our true airspeed. So I'm getting about 192, maybe 193. But again, if you're within 1, that's not going to be that big of a deal. So we'll try that out. 192, of course. But anyway, that's all stuff that you can practice, and I recommend practicing to get comfortable. Try to do it soon so you don't forget everything. I did send you some, uh, I'll send you the slides, but you should have a copy of the uh, stuff I printed out for you there. So, do, 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 do. Uh, which I know these slides are a little busy, but it kind of just shows you, just the number 1, the number 2 steps, and the arrows kind of show you how to set things up. But also just remember, a lot of the directions are right on the front of the E6B. So next week we're going to do a flight planning exercise, and you're going to want to have with you the pencil, some pencil, paper. I'm going to send you a copy of the flight plan form. Maybe you can print it out if you can. You're going to want your E6B handy, calculator maybe, your plotter. I'm just going to show you a couple of plots, and then I'll be doing most of them because I know most of you don't have sectional charts. But if you do have a sectional chart, we're going to be using the Detroit sectional chart so you can follow along on that. Other than that, if you got any questions, pop them up now. Otherwise, I'm going to sign off. Oh, all right, guys. Thank you. I think the battery died on my camera, but we'll get that fixed for next week. Thanks again, everybody. Have a good night.